In this lesson, we'll define the moment of a couple, and we'll show how to calculate it using both a scalar and a vector method. Now recall that the moment of a force is simply the force times the perpendicular distance from the point to the line of action of the force. And so this force applied to the handle of this wheel will tend to rotate the wheel in a counterclockwise direction. A couple moment, on the other hand, is two equal and opposite forces that do not lie along the same line. They create a rotation as well. Each force creates its own rotation, and the total, of course, is then given by the moment of the couple. Actually, you apply a couple whenever you turn the steering wheel of a car, or in this case, a tractor. And of course, in this case, it's a clockwise couple. Finally, here's an example of a couple moment which tends to turn the screwdriver and tighten the screw. Now let's compare the effects of both a force and a couple. When a force is applied to a body, it will cause the body to both translate and rotate. If you apply a couple moment to a body, it will simply cause the body to rotate, and it won't translate. So couples essentially just create pure rotation, or a tendency for pure rotation. Now how do we find the moment of a couple? Well, we'll begin by using a scalar formulation. First, realize that a couple moment is a vector quantity, which is equal to the magnitude of one of the forces times the shortest distance between the two forces. In other words, the perpendicular distance d. The direction of the couple moment is found using the right-hand rule. This couple moment tends to rotate in this direction. So if you curl your fingers like this, the thumb will be then directed in the direction of the couple moment. Of course, that's perpendicular to the blue plane that contains the two forces. Now here's a couple moment in two dimensions. The magnitude of the couple, of course, is F times d. In what direction does it act? Well, the forces tend to rotate around each other in a counterclockwise direction, like this. And so if you curl your fingers in this direction, the thumb will be directed out of the screen. That's the direction of the couple moment. Now there is one important thing about a couple moment, and that is that it's a free vector. That means that it can act anywhere on a body and still produce the same effect. If you apply the couple moment at this end of the beam and calculate the reactions, and then you move the couple moment to some other point, you'd still obtain the same reactions on the beam, whether that point be in the middle of the beam or even at the other end. Anywhere you place the couple moment, you'll always get the same reactions. Couple moments are free vectors and can act anywhere and create the same external effect on a body. And there's one other important thing about a couple, and that is that you can calculate the moment of a couple by finding the moment of the couple forces about any point you want on the body, or even off of it. Let me give you a simple example to illustrate what I mean. Here we want to calculate the moment of this couple about point O, and we want to also calculate it around point A and also point B. So let's do each one. If I calculate the moment of the two couple forces about point O, I have the following. First, I have 200 times the moment arm of 3 meters. That, of course, is the moment of this force around this point. Now the moment of this one. That, of course, would be negative, won't it? Minus 200. And here the moment arms is equal to 9 meters. When I work this out, if I get my result, it turns out to be minus 1200 Newton meters. In other words, the couple moment is directed into the screen. Now let's calculate the same couple moment about point A. If I do that, the moment of this force around the point is 0, and I only have the moment of this force, and that will simply give me minus 200, and now the moment arm distance is equal to 6. But when we work this out, again we get our same result, minus 1200 Newton meters. And finally, we'll calculate the moment around point B. Well, again, the moment around B is going to be in a clockwise direction, so it's negative. And I have one more time, minus 200 times 6. And so again I get the same result, minus 1200 Newton meters. Regardless of what point I choose to calculate the moment of both forces, I always get the same answer. Certainly the best choice would be to simply take the moment around a point which lies on the line of action of one of the forces, and that way you only have one term to consider when you calculate the couple moment. But basically, the couple moment is simply equal to one of the forces times the perpendicular distance between the two. And of course, you get that answer of 1200 Newton meters, realizing that the couple moment goes in this direction, clockwise, and is therefore negative. All right, now let's discuss finding the moment of a couple using a vector formulation. Let's start with this couple, these two forces which are equal and opposite, and not along the same line of action. We can find the moment of both forces by selecting some arbitrary point O in space. In order to find the moment of the forces, of course, we need position vectors going from O to the line of action of each force, like R sub A for this one and R sub B for this one. When I calculate the moment, of course, I have an R of B crossed with this F, and of course an R of A crossed with minus F. I can factor out the common force term. When I do that, I simply have R of B minus R of A crossed with F. This is the distributive law of the vector cross product. Next, let me extend a vector R from point A to point B. In other words, this one. Then I can make the following statement, that R of A plus R is equal to R of B. I then realize that R is really equal to R of B minus R of A, and I can substitute that into here. And when I do that, I get this result. M of C, the moment of the couple, is simply equal to R cross F, where R is a vector which can extend from any point on the line of action of one of the forces to any point on the line of action of the other force. In this case, the R is directed to this force F. Obviously, the moment of this force, minus F, about point A, would be equal to 0. So essentially, I'm finding the moment of a couple by simply taking the moment of both of these couple forces around this point. 0 moment from this one, and r cross f for this one. Realize then that I can get the answer if I use a determinant. And of course, the first row is ijk, the second row are the components of my position vector, and the third row are the components of my force vector, the force to which r is directed. Always remember that. And so to make sure you fully understand the idea, here it is again, r cross f, where one more time, our r vector is directed from any point on the line of action of one of the forces to a point on the line of action of the other force. And remember to use this force when you do the cross product. This r will work, of course, but so would this one, or even this one. They all come from the line of action of this force and go to the line of action of the other force. If you want to, you can also go the other way and say it's r cross minus f. In this case, this r would work, and so would this one and this one. Again, you have to use minus f here because that's the force to which r is directed. Now let's use these ideas before we end the lesson to solve a basic problem. I want to determine this couple moment. Obviously, you can see it very quickly, I think, using a scalar method. We have 6 newtons, and of course the distance between the two couple forces is 4 meters. If I use my right-hand rule, I think you'll see that the moment of the couple is simply 6 times 4, or 24 newton meters, and by the turning of the couple, meaning it rotates this way, and curling your fingers in that direction, the thumb will be directed in the minus I direction. And so since that's the case, the moment of the couple is then minus 24 I newton meters. But we're going to do it using a vector method. Therefore, I have to set up a position vector, going from a point on the line of action of one of the forces to a point on the line of action of the other force. Consider this one as a possibility. But you know we can also use this one and solve the problem. I'll do it that way, because after all, this is the easiest one to use. And so in doing it, I simply write this out as r, in this case, 4j, and I'm going to cross it with what? This vector, right? Minus 6k. Obviously, when you work this out, 4 times minus 6 is minus 24, and j cross k is equal to I. So I get my result. Of course, I can also solve the problem by going the other way. For example, extending a vector from D to B, or even one from D to A. Here the r would equal minus 4j, and we're directing it to the force 6k. The cross product gives us minus 24I. If you don't like doing it like that, you can do it like this. You can take the moment of both couple forces about some arbitrary point, other than a point on the line of action of one of the forces. So here, to get the moment of the couple, you would simply say this r crossed with this f, plus this r crossed with this f. Add up all the components, and bingo, you get the same answer. But that's a lot of work. All right, finally, let me discuss resultant couple moments. If all 3 of these valves were tightened at the same time, then there'd be 3 couple moments applied to this housing. But how would you find the resultant couple moment? Well, it's rather straightforward. On this block, for example, all you'd really need to do is to add the couple moments together, and you get the result. It's really that easy. Remember, couple moments can be placed anywhere, so that when you bring them together and add them up, that resulting couple moment will produce a reaction at the support, which will be the same as all 3 couple moments acting on the block. It really doesn't matter where the couple moments are located when you want to find the external effect of a couple moment. It's a free vector. And so on that point, we'll end the lesson.